Hi there, everyone. Welcome to First Principles. Today we've got God with us, and we'd be speaking about the first principles of physics. How are you doing, Godwin?
Yeah, doing really well. How are you?
Very well, thank you. For the context of this episode, could you introduce yourself to the audience?
Yeah, so my name is Godwin Madho. I did an undergrad in physics with astrophysics at the University of Leeds. Then I did a PhD in fluid dynamics and rotating systems. And then the pandemic happened. Stuff went out of control. And now I work as a data scientist.
Okay, well, still related.
Yeah, still related. I use all the critical thinking, everything I learned, more or less.
Yeah, yeah. Okay, so the first question, diving straight in, what is physics?
Physics, I think, as the name suggests, is the description of what is physical, what we can see, and in the modern sense, things we cannot really see unless we go to the microscopic level.
Hmm.
But if physics started with the ancient Greeks, I guess, for Western civilization anyway. Although human beings have been doing this for ages, right? We humans have always been curious creatures, so the curiosity is what drives us to invent science, I
Yeah.
guess, and discover the world and put descriptions to what we're seeing.
Hmm.
And I guess physics essentially we made as a way of describing what is physical.
What is
And I
physical?
guess
Yeah.
and I guess that's what the name comes from.
Okay. So in that context, and this might be putting you on the spot, I don't mean to do that, but just from my understanding. So
Mm.
biology is physical as well, and chemistry is physical as well. So
Yeah,
what's
yeah,
the
yeah.
what's the defining line?
I guess I guess so. Everything. I guess if you talk about the pyramid of I guess science, it will be mathematics sits at the bottom,
Hmm.
which is the foundation of everything we do. Then I guess on top of that is physics, and then on top of that is chemistry, and top of that is biology.
Hmm.
I think that's the right way of doing it. Whereas
Right.
people might disagree. Some there might be some controversial. This
Yeah.
is my hot take, I guess. That math is at the foundation, and then biology at the top. And I guess the fundamental laws of physics then drive what is happening in chemistry and what is happening in biology, essentially on a bigger scale.
Hmm.
So the fundamental laws of physics are essentially used to like describe the other activities higher up in chemistry and biology.
Okay. And then does philosophy come here in some form or the other? Because I always wonder if philosophy is like the first subject, or is maths the first subject, or are they like parents and then everything springs from there? Do you have any opinion
Yeah,
on that?
I think philosophy and maths are parents. They're I guess the daddies are the mothers, I guess, of all these things, because it all starts with a question, and is, I guess, philosophy is a word way of saying what is happening, and then mathematics is the numbers way of saying what's happening. I guess that's a
Okay.
good way of putting it.
Okay.
Um, yeah, like we think about, I guess, ancient scriptures in many cultures have these sort of stuff where they talk about things, even like be it the Vedas or the Bible, when they talk about different things,
Hmm.
there's like measurements and stuff that they give in words. And you can put those in equations that people try to put in to figure out what do these things actually mean.
Yeah.
So yeah,
Okay.
one thing drives the other. I guess they're both a slightly different language of saying the same thing, I guess.
Yeah. So I'm assuming philosophy is going to be much more verbose than maths because it can, the specialized language of numbers and equations, they get to the point quickly.
Yeah, yeah, yeah. It's just one equation, right? And in philosophy, you have to write a paragraph to explain what's happening.
Yeah, yeah, yeah. Okay, so before we dive a little bit deeper into physics, I do have a few more comparison questions. So I was trying to read this book. I'm not forgetting the name now. I think Kevin was some guy. I'll come up with it later on. But I think it's called The Language of Mathematics, where the author is comparing, like, let's say you go to a concert. Now, if you can't read music, assuming you can still hear, you'll get the output of it. But with maths, if you don't read music, but whatever, they read the mathematical equations, there's no way for you to actually get the profundity of what's happening over here. Now, I feel that needs to be addressed somehow with this AI or whatever is coming in. But the related question to that is, do you think maths is invented or discovered? Because then that has
Oof.
implications for physics.
I guess this is both a philosophical question as well, right? Is maths invented or discovered? Um, I think all of maths is invented because for me, mathematics is an idealized version of what we're actually seeing because we can never have all the different factors put into mathematics because we never know all the different factors that influence something.
Hmm.
Um, And I guess so. I guess a mathematics is a simplified way of showing what we're actually seeing in physics in a physical system.
Hmm.
So in that way, I guess it's invented slash somehow discovered and then invented into be like we discovered this thing and then we invent the mathematics, I guess, to describe it.
Right.
I guess that's one way of putting it as well. We discover something and then we create the mathematics to describe it.
So we induced, in the sense, like in the philosophical sense, you see the concretes, you abstract away, and then of course the abstractions can float as well, but for some reason they're still grounded to reality.
Right, you make it the mathematics, you can use it to make it concise, and then this is and it comes down to like this is the simplest way of describing something in this physical form or in this system, or for this solution, for this problem, this is the mathematical solution for it.
Go ahead.
And I was going to say, and it only works in an idealized solution as well, because we never know everything about the world. So there's always different factors, and chaos always plays a role in real world, right? So
this itself is also like a philosophical statement, and I assume mostly for the Western culture, because there are other cultures who believe we know everything that is to know. I don't think that's true, but this starting point, like the knowledge is yet to be, we still need to keep discovering knowledge, is a fundamental at the whole driving force as well. Like, why do you keep doing whatever you're doing?
Because there's always like something fun to discover, and I guess something to describe. That's what you keep doing it, just curiosity, really.
How much of mathematics do physicists basically borrow from that subject, and then where do they diverge?
Oh yeah, this is a really good question, because I guess you invent mathematics as well in certain sense, because I mean Newton did that, right? He invented his own mathematics to solve his equations. Right. So in many sense, mathematicians, because they're so pure in their interest of just learning new numbers and having interesting descriptions of this interesting, how would you describe it? Like interesting cases of how patterns are seen, how things happen. So mathematics are doing their own thing. And I guess the physicists come along and go like, oh yeah, this equation that you're seeing here, it actually describes this system quite well. And then you essentially borrow it, right? And then you do some more iterations on it. And then you can have your own branch of like, oh, we're now not only using this borrowing mathematics, and then now we're inventing mathematics as well to further enhance our understanding of a system. So a mathematician would have invented something that describes a certain situation that he's thought about, right? But then physicists would come along, be like, oh, I see this thing, and that looks very much like this thing that you have described. So we borrow it, and then we refine it, we like add more stuff to it, reinvent it maybe a bit more, and then just go along and describe the system. So I guess it's borrowed and then refined in mathematics.
Okay. So it's a symbiotic relationship.
It's very symbiotic. And I think in a lot of times there's also, because I guess one of the big things, so I did my PhD in the maths department, so I now understand their side as well. And there's a lot of like, to and fro between mathematics and maybe other science people, where it's just like, what you guys are even doing? You're just like looking up the numbers and stuff. But curiosity and things that they invent will always be useful further down the line, because there's always be situations where the patterns they have seen might reappear in the real world, and then you have to be like, oh yeah, thank God someone did this like 100 years ago. Now I can use this, right? So it's always a good thing to keep the mathematicians, encouraging them to do their own thing, because we never know when they discover something that will be useful to us.
I mean, I guess with I think before the call we were talking about the von Neumann machines, and computing found a great ally in Boolean algebra, which was invented quite a while ago. So that did not come, it was just lying there, and they just started using it. So that's interesting. Is there a proto-physics, like before physics came by as a formal discipline? What were people doing? It just helps me understand the evolution of it.
I think if we talk about evolution of physics, I guess for me, the oldest form of physics must have been astronomy. Because people were obviously being like, oh, it's nighttime, daytime. That's how it starts. And now we're suddenly being like, oh, now weather patterns are changing. What's happening there? So we're trying to keep track of that. Suddenly you're looking at the stars and being like, oh, when this star comes out, then this happens in my local area, sort of thing, right? So you're starting to do astronomy and then using that to predict what's happening in the future or what's going to happen in your local area, if summer's coming, if winter's coming, if there's going to be rainfall, that sort of stuff. So I guess astronomy could be a type of proto-physics that cavemen used, and then that influenced, everything else from like navigation to like how do we like put sticks together to make a house. So I guess it like started from those kind of things, and then here we are today.
Yeah.
Magic.
Yeah, magic. Yeah, because hit and trial. I mean, of course, I don't want to conflate physics and engineering, but it's just important to remember that, I mean, these are distinctions, taxonomies we made up because it's it's not as clean as like a floating abstraction coming, oh, now it has practical applications. Sometimes you get the abstractions from the practical applications. All right.
Exactly. Okay. So it's all like flows naturally from one thing to the other, right? Because one person goes, oh, how do I navigate using the stars? And they're like, oh, okay, maybe I can use the stars to predict the weather or something, or the season. And then you start like measuring time suddenly, and you have calendar years suddenly being invented. Then someone's like, oh, I need to make a clock now to like measure this thing. And, so it just flows into one thing or the other. And, everything is then invented from like one thing or the other, right?
Okay.
You get engineering, you get chemistry, you get biology, just like coming from one thing or the other.
Yeah. I mean, I have some interest in architecture as well, and they have a term called vernacular architecture, which is probably means that you don't have like a formal engineering drawing or whatever in that formalized way, but it worked. So it's great to study it and then use those principles to get something beautiful out there. Perhaps similar. Okay. Natural philosopher was also a term used, like in the olden times, to describe a scientist, but I'm assuming to describe a physicist as well, being that it's a branch of science. So, would you know, like, what prompted the change of term? Was it just like the body of knowledge expanded and you needed specialists?
Yeah, I guess so. I think natural philosophers. I think people at some point, I would guess, in the Renaissance era, diverged from like doing everything where a natural philosopher would talk about biology, chemistry, and physics and mathematics as one person would diverge into like, oh, this guy just does this guy just chemicals, this guy just does biology. And I guess that's the time when the Renaissance happened. I guess that's when the divergence actually started.
Okay.
Because I don't know if Newton called himself a natural philosopher or I think they were still called. I think if you go to Oxford, you can still do a degree in natural philosophy.
Oh, okay.
I think you can still do those things.
Great. They keep up with their traditions, don't they?
Yeah. I mean, it's oldest university in the UK, I guess. So yeah.
Yeah. Okay. Now, let's go back to the definition: seeing physical things. Now, obviously, our eyes and the sight is limited, right? So we talk about atoms and I don't know what else, right? In the macroscopic scale and in the thermodynamic scale and in the microscopic scale, we're not technically seeing it physically anymore. So what kind of gymnastics we need to sort of do in order to include whatever current physics is happening within the definition of physics? So is there an expanded definition?
I guess the expanded definition at the moment is probably everything which is non-biological, I guess.
Non-biological. Okay, so chemistry would be included there.
Yeah, in some sense, chemistry would be, although there is also biophysics. So we still do stuff like fluid dynamics and fluid flows in the body. So there's still that's still there. But yeah, in some sense, it is. I guess physics describes everything that uses the fundamental forces of nature.
Okay.
Right?
Okay.
Maybe that could be a more formal definition.
Okay.
Maybe. Yeah.
Yeah, I like that definition. I will basically double click on the fundamental forces of nature because that's interesting, and I guess that's the point. But before that, let's a few more tangential things. What kind of university disciplines I have seen is there's physics, like a BSc in physics, and there is also applied physics, which I don't know how that is different from engineering. So enlighten me. And there's the theoretical physics, which basically is like what, maths and magic. So what is the difference between these three?
I guess it just depends on like what university is teaching you and what modules they want to teach. Really, there's nothing.
So it's also branding. So
yeah, it's also a bit of branding as well. Like theoretical physics, you'll do a lot more stuff which is not experimental, I guess. So it'll be more mathematical, like quantum mechanics. You'll do a lot of that. You'll learn a lot more about hard physics, just like tensors, how to multiply giant matrix systems, all these kind of stuff. In theoretical physics, fluid dynamics, you'll do a lot of fluid dynamics,
Hmm.
learn the basics of that. Normal physics will just be like some experimental stuff. You'll do the basics essentially. You do the foundation of everything, A to Z, soft matter, to astrophysics, to like quantum mechanics, to like nanotechnology. You'll cover all these things.
Hmm.
Applied physics usually tends to be more engineering focused. I guess, how do you actually, what's the physics of making an internal combustion engine, for example, something like that. So how does fire work? How do you simulate something like that? How do you simulate water flowing in the river? How do you simulate geological systems or geothermal systems? Some stuff like that. So
Okay.
I guess that could be a distinction between the three. But
Okay.
it's usually depending on like who the lecturers are and what they study and what the research background is. They can just put stuff up and be like, I want to teach this thing.
Right. Got
Right.
it. Got it.
So
Yeah.
there's
Yeah.
no formal definition of like this needs to be in here if you're going to teach theoretical physics or applied physics or just physics.
Yeah, yeah. Okay, so I mean, it's curious because like UK generally has 3-year degrees, and
Mhm.
when I at my time when I was there, theoretical physics was like a 4-year degree on its own, and people used
Yeah,
to
yeah.
another popular joint honors, I mean, in the US that's not really a problem because there's a major and a minor everywhere, but in the UK you kind of like you decide what you want to do beforehand, kind of, and then they had joint honors in physics and philosophy, so that was
Mhm.
interesting. Some had mathematics and philosophy. Maybe I'm like making the second one up, but that that synergy is I guess
Mhm.
interesting. I One thing you said about studying gas systems and studying the internal combustion engine, perhaps engineers would be figuring out how to optimize it better or how to sort of focus on invention in some other way. Although I don't think a lot of engineering is very 0 to 1 focused because, and that's sad, but whatever. It's mostly about tinkering. But perhaps in applied physics, they are trying to abstract away how something which came into existence through trial and error or through some design and additional trial and error. How does that work? And if we can abstract away the knowledge from actually human invented things, maybe that's a useful distinction between applied physics and engineering. What do you think?
Yeah, I guess you could do like material sciences as well. How do you actually,
Mm,
if you take the ideas of physics and how do you actually put it in a real world system and be like, okay, I need to, if the water is flowing this way, if I make a dam,
mm,
then I can actually capture the flow of water and then I can make it flow this way and then I
mm.
can get some energy out of it. So you're taking the ideas of fluid dynamics, you're taking the ideas of the forces of water and how water affects the surrounding, and then applying it to make energy at the end.
Okay.
So I guess something like that could be a
Yeah.
way of thinking about it.
Okay. So one thing, just to, I mean, a caveat for myself and the audiences as well, just because something branched out from something does not mean that the child, let's say the daughter branch thing is not going to become like big on its own, and then later they can combine.
Mhm.
So like, I guess that's what biophysics is, right? So this is
Yeah, yeah.
combining an older discipline and a newer discipline comparatively.
Mhm.
Okay.
Yeah, definitely, definitely. Like engineering is same as that, right? There's a lot of physicists who go into engineering later on in life
Hmm.
to maybe do something applied that they had done in undergrad or PhD,
Hmm.
and vice versa as well. Engineers come back to physics and do more, maybe some more theoretical stuff, or join a physics research group to do something else,
Yeah.
even though
Yeah.
they have an engineering background. So yeah.
Yeah, these distinctions and these taxonomies are useful for like human cognition, but we need to
Mhm.
understand that these aren't like hard walls. They're very
No,
permeable
no.
walls.
Yeah, yeah, they're very fluid. Like you can. I think once you know science, you can apply it to any field, right? So
Right.
once you know the fundamentals of science, I guess once you understand how science works, you could apply it to chemistry, you can apply it to biology, apply to like the amount of people I've seen who do STEM degrees and go to banking. Like
Yeah. Yeah.
how do
Yeah.
you, how do you do that? You don't, yeah,
Yeah.
we don't learn accounting in physics,
Yeah.
right? But a high percentage of people who do physics end up in the banking sector because they know maths, because they
Yes.
know they know critical thinking. They do all these things that you learn when you do a STEM degree can
Yeah.
be applied to other sectors in the world.
Yeah. I'm gonna insert a little rant over here. Like, univer universities are not trade schools. Trade schools,
No.
you learn a trade and then you basically do
Mm.
that, assuming there's a market for the rest of your life to do that, which in a dynamic situation, that's not the case. In university, you're going to study fundamentals, critical thinking, learning how to learn, and ideally, school should also be like that, of course, along with the vocational subjects. But this academic part is important. So to me, it's great that people trained in physics want to go work in banking, which means they'll be more in touch with reality rather than just something happens and the economy crashes. So
Yeah, yeah.
yeah, because even wealth creation, and wealth by wealth I mean like goods and services, like physical goods and services, but that's pretty physics grounded. I mean, that's the whole
Mm.
point of it. Okay,
Yeah.
yeah.
Yeah, definitely. Like I don't have a background in data science.
Hmm.
So I did a physics degree, I did some mathematics, and then I essentially did a year's worth of training by myself, teach myself data science and machine learning,
Hmm.
and now I'm here. So yeah, all the knowledge I gained of critical thinking, self development, learning by myself, how to like prioritize tasks. This is
Yeah.
what got me to here as a data scientist.
Yeah. And you did it on your own. So that also, like, even designing the curriculum
Well,
for yourself is a big deal.
yeah, yeah. I mean, I got a lot of help.
Sure,
YouTube
but
is there, internet is there. So
yeah, yeah. Yeah, but like you could float away, man. I mean, you don't know like how much general principles you need to know, where you need to draw into the specifics. All of those things has to be somewhere inside in a conceptual framework, isn't it?
Yeah,
Yeah.
yeah, definitely.
Okay. Now, again, I'm still waiting to get to the fundamental laws of physics, but before that, again, do you have any? Now, I gave you like a false distinction, like a branding distinction between theoretical, applied, whatever. But are there any real distinctions in the sense of what you're studying? Like I said, the thermodynamic scale, the quantum scale, and the astro scale. That's one sort of triad I can think of. What other things that you can think of?
Well, the distinctions aren't there really because one set of equations can be useful um, to talk about a big thing like the universe, and the same equation can actually be used to do quantum mechanics as well. So in the same sense, because there's I think people are still working on this, but like quantum field theory, string theory, all these things are meant to be um, connecting the different types of physics that people do, just like you said, quantum mechanics, be it like astrophysics, be it general relativity,
Mm,
be it thermodynamics. There's a lot of research happening on how to attach one thing to the other, because in reality, one thing all affects the other, but we don't really know how to go from one side to the other in one smooth fashion. There's still barriers in place in terms of how we can derive one thing from the other from
mm,
fundamental principles.
mm,
Um, but we know what it should look like at the end. We know what it should look like at the beginning. We somehow know also what it looked like at the middle. But is there still the connecting tissue is still missing? And there's a lot of work still happening in that sort of sense. But there is no hard barriers between using equations to describe one force to the other. You'll just change the terms maybe, or like add a term, or like take away a term, because like this term does not affect this thing at this scale, and this term goes to zero at this scale. This term goes to infinity at this scale. This term goes to 10 at this scale. So it's just a matter of scales, but the fundamental equation stays the same.
How many scales can you think of? So I gave you three, but do you disagree with that distinction?
No, I think it's fine. Like macro, and then micro, what we can see, what we cannot see. Sorry, micro, what we can see, and then the macro scale, I guess, of the universe, right? So yeah, I guess these three are the simplest way of like
Yeah.
dividing the world, right? So
Yeah.
it's
Okay.
not too bad.
So you said the fundamental principles of physics. Now I think this is the time where we need to talk about them. What are they?
Oh, the hard stuff. Oh my God. So there's obviously I might have to actually Google this because
Oh,
I sort
absolutely.
of
Yeah,
I
yeah,
don't want
yeah.
to like mess this up, because we know there's gravity, there's electromagnetic stuff, there's also quarks and all that kind of stuff. So let me just quickly get it up. I should have done this before we started, right?
Oh, no, no. Are you describing the standard model over here? That
Yeah,
current
yeah,
state of
exactly.
the art?
Yeah,
Okay.
the standard model, right?
All right.
Um, that's probably the best way of describing the fundamentals of physics and the gaps that we also have in the fundamentals of physics. Uh, bu- 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 it's just given me the wrong thing already. It's given me like some AI stuff, which I did not want. This is what happens when you stop using physics and look at machine learning instead. Google just goes, "Oh, you didn't mean that, did you?"
Yeah, no, no. I meant that. Google needs to understand that what I mean. Yeah.
But so we have, now that I've got it up on Wikipedia, uh, gravity, electromagnetism, weak interaction, and strong interactions. These are the four fundamental forces of nature. And I guess everything else is built upon that. And there's still a lot of research going on. I mean, famously, the Higgs boson was only discovered like just about a decade ago now, right? So
And the Higgs
just over a
boson,
decade ago.
is that a new force or does that fill into these four categories? Weak.
It fills into the four categories. So essentially, the Higgs boson is something that was theorized that gives mass two things.
Right.
So we only have mass and we weigh something because of the what's called the Higgs field
Right.
uh, that permeates everything.
Okay. All right. Now, to the extent you're comfortable, can
Mhm.
you give me like a elevator pitch or little bit more on these four things? So electromagnetism, gravity. This I remember from school actually.
Mhm.
Then the strong forces and the weak forces. I guess you said strong interactions and weak interactions. Those
Yeah,
I don't
yeah.
really remember. So what is why are these four things not like one? I mean, if we believe in like a monism or like a non-duality,
Mhm.
and if they are these four things, like what are they? Let's start with what are they?
So these are sort of mysterious forces. So there's still stuff happening, right, on research trying to understand where these forces actually come from.
Hmm.
Um, and I guess some of these forces we think are because of fundamental particles like electrons and quarks, and how they interact with each other. I think weak interaction is, as the name suggests, very weak, but it's related to radioactive decay and how that affects the world around it. Um, so yeah, there's still a lot of like work happening in these sort of situations where they're trying to figure out what it is actually that creates these interactions and creates these energies and what actually makes the atom tick, I guess.
Hmm.
Because
Okay.
quarks are like a brand new concept as well, right? I mean, 100 years ago, we were talking about just, and I guess people didn't even know about atoms, right? It was Einstein who first thought, I guess, he won the Nobel Prize for it,
Yeah.
for doing the atoms. And then we went to electron, protons, and neutrons. And now we were like, oh, protons and neutrons are made of quarks. So there's more fundamental stuff in there. And then quantum mechanics happened all of a sudden. And then everything's upside down, everything's spinning. There's like stuff happening. You can't tell.
Hmm.
You can know one thing, but not the other thing. And now you're just like all up in the air.
Yeah. But is it
So
really up
there's
in the air, or is it just we're trying to muster up and figure out what really it is? I mean, is it like gaps in our knowledge, or is it actually up in the air?
I mean, there's definitely gaps in our knowledge where we're trying to fill in why are certain things happening in terms of experiments that we see.
Hmm.
Why are certain things happening when we look at the small scale, like how do neutrinos and all these things actually interact with each other, and how did they affect the world around us? On the big scale as well, how does the expansion of the universe actually affect what's happening? How does the Big Bang actually evolve to what we know the world to be today? There's a lot of things happening. Supermassive black holes were theorized years ago, but only discovered recently.
Hmm.
Black holes were theorized 100 years ago. Einstein did not even believe that it could be a thing, and then we discovered them. So I guess he was proven slightly wrong that his own maths could do that sort of thing. So yeah, there's a lot of mathematics that tells you what things are possible, but are they actually possible in real life? That's the question. So there's a lot of discoveries to be made in that
Yeah.
sense.
Yeah. I'm
And in a
here.
lot of
So
you're
go ahead.
good. I was going to say there's a lot of like also discoveries that we think are out there that we haven't put down on paper. Dark energy and dark matter being one of the famous things, right? Where we think there is all this universe to discover and we still don't know what they are, what
Right.
it's made out of.
Right. Okay. And we don't know what the full map is, so we can't really say how much we know, right? We can't say it's
Yeah, yeah,
30% complete. We don't know. Maybe
yeah.
it's
We don't
100%
know.
complete, but it doesn't
Yeah,
feel like that.
yeah. Maybe we just haven't discovered how things connect to each other yet in a
Yes.
fundamental sense. So
Okay, so what I'm hearing is you talked about fundamental particles and fundamental forces. Now, this is basically a little like this is the energy and this is the material. I'm going into
mm,
some other esoteric,
yeah,
even spiritual traditions, which I think have sort of informed the study of matter as well. Now, yeah, of course, in the modern times, we keep it separate because we don't want to get into dogmatism. But hey, if if they merge at some point, they merge at some point. Whatever is real is real.
yeah. Like I mean, we know Einstein's famous equation: E equals mc square.
Yeah,
Energy is mass, and mass is energy. So one thing
right.
can be converted into the other.
Yeah,
And it's perfectly fine. So, and as like the laws of thermodynamics is also, you can't energy cannot be created or destroyed. It just gets changed into one form into the another form. So,
right,
so
right.
it's like really symbiotic with what Einstein said. So it works quite well.
I'll come back to the energy cannot be created or destroyed and figure out how that basically equates with the whole concept of entropy, because I think the whole point is everything is getting destroyed. But like at least becoming into like a big soup where there is no equilibrium. But let's just go to the four forces again: strong forces, weak forces, electromagnetism, and gravity. Gravity. Right. Now, do all these four forces have separate particles for them, or the particles are also like they can be used by these four forces separately? Like, are there any, do strong forces have a separate set of particles and weak forces have a separate set of particles and EM? How does that work?
Yeah, so I mean, if you go to Wikipedia, there's a really nice, really nice diagram of like the different particles and which forces they're connected to.
Mm.
There's a really nice diagram for that. If we just look up standard model, there's a really good diagram for that. Yeah, I mean, this could get really technical. There's like fermions,
Oh,
there's bosons, and all these kind of stuff, which make up all these fundamental forces.
okay.
So we can go down that rabbit hole of like
Oh,
quarks and leptons
I
and
don't mind.
bosons. Can
I might not understand it, but I don't mind. It's
I mean,
worth an
I don't
exercise.
understand most of it because this is where you get to the theoretical physics side, which I did not do,
Right.
and because a lot of research at this level happens when you're actually doing a PhD or you're actually doing theoretical physics or
Mm.
doing a postdoc. This is now where you're actually learning about these really fundamental things,
Right.
and you're making your own experiments, maybe using some lasers or something in a quantum mechanics lab somewhere hidden in the corner in the dark. So this is the kind of stuff that you're doing there.
How much of the standard model is, excuse the naivete, but real?
I mean, all of it is real. We can measure these particles. So if you go to a particle accelerator, if you look at diagrams from the CERN reactions and experiments, they can tell which particle is what, right? In like 90% of the cases, I would say they know. And that's, I guess, how the Higgs boson was discovered, because they were like, okay, the equations say at this point we should get something like the Higgs boson, and that's what they were leading up to.
Mm.
And they finally found it in the data, and they were like, okay, this is the Higgs boson because we found it. The equations predicted it was used to be should be this at this point, and with this energy, this mass or whatever.
Mm.
And now there's another phase of upgrades happening to even break it down to understand a bit more things.
Mm.
So each particle that we have found so far has a mass or like a spin or like a electromagnetic charge, you know, that sort of stuff. So we measure these things using those things, and we know one or the other, and then we can tell what's happening in there.
So we're getting a lot of engineering help as well here, I'm
Yeah,
assuming.
yeah, yeah.
Okay.
Because you need to do a lot of engineering, a lot of materials engineering to make sure you can withstand that sort of pressure in a vacuum as well. It has to be in a vacuum as well. I did when I was doing my PhD. It was related to fusion energy. So I was talking to a lot of fusion engineers and material engineers who were trying to figure out what size of magnets do we need to make sure these plasma beams stay in the
Mm.
center and they don't deform and then damage your fusion reactors and all that kind of stuff. So there's a lot of work how to create superconductors, powerful magnets, how to create all these like things that we'll actually need in the future if you
Mm.
want to survive and be in a fundamental sense of stop using fossil fuels, stop using these kind of things, and go back to renewable stuff.
I would actually say, I mean, I owe a great gratitude to fossil fuels for making the modern life possible. So, but
Mm.
yeah, survive is one thing, but like going up the Kardashev scale, which I would like to do, type one, type two, type three, type four civilizations, I don't know if fossil fuels can get us over there. So this is going to be important stuff. By no means like going back to nature and the degrowth thing. I don't want to be going back to nature, but maybe in a very fundamental level of universal nature for sure. Tell me this, the fundamental forces that you describe and the fundamental particles that you describe, is this a safe assumption to have that those won't be seen as very fundamental, after a while when we make new discoveries? Can there be like a unifying thing, unifying all those particles and unifying all those forces? Is that, I know it's speculative, but what's your what's your
uh,
speculation?
I don't, like for me, I have no credentials to talk about it at all. So I feel like I mean there could totally be like more physics in there that we can discover, like, oh, we can even break down these quarks into smaller things because we've already have like weird stuff like up, down, charm,
Mm-hmm.
strange, top,
Yeah,
bottom, these sort of things.
yeah.
um, so it could still be that we break them down into even more things, and maybe in some sort of way we find something really fundamental in there which starts the spark for all of these things to happen.
Yeah, yeah.
So that could still be a thing, but that's probably still far away.
Yeah, or not. I mean, we don't know. Like
Yeah, we
when
don't know.
somebody
Yeah, yeah.
gets that dream and figure it out. I guess Where do you think these ideas come from, though? Because I don't think this is really just pure deduction or induction or rationality. I mean, yes, that is a good sort of mixer to put all of these, I guess, influences in and figure out how they fit into the larger picture. But the fundamental ideas sometimes are communicated. Like very famously, I think benzene had that. The
The
person who
benzene
invented
ring.
the benzene ring was like a snake eating itself. I think that's the story. I don't know if it's true or not, but that's how he said he did it.
He dreamt a snake eating its own tail, and then I was like, oh, that's what it is.
Yeah, yeah. So that could
Yeah.
happen, right?
Yeah, I mean, famously, Schrodinger came up with his equations while he was, having sex with his mistress in Switzerland somewhere. So
Yeah,
that's apparently the story. Anyway, there's a great
yeah.
book about that. Uh, but yeah, I mean, when you're when you're really deep into a topic,
Hmm.
these ideas can come out of nowhere, right? You could
Yeah,
be, you could be. I remember when I was doing my PhD, I was really stressed about like some stuff not working, and I would go to bed and I would dream of just like being at my computer typing away my code, and then suddenly going, "Oh yeah, this is how I should have written it," and then doing it the next day when I went to the office.
yeah,
So when people are really into, and I mean, it's not just physicists, right? It's like every artist also like has that situation.
yeah.
Countless musicians talk about they were thinking
Businessman.
about, yeah, yeah, whoever, right, writers, whoever, they just go, oh, I had a dream about this, and then I woke up and did it, and I was like,
Yeah,
this is great. So I think it's just a matter of how much are you thinking about it, and then subconsciously your brain is also still thinking about it, even though you might have gone to bed or doing
yeah,
something else, and then
yeah.
subconsciously just like there's a click somewhere, the puzzle pieces just fit suddenly, and your brain just goes, ah, yes, you should have done this thing.
Yeah, yeah. I guess the best
But
citation is, I got it in a dream. So,
yeah, exactly. But I mean, with the particles in general, I think it started off because we just thought of, why don't we just smash the particles, right? So when I guess it all goes down to good old hydrogen bombs and fusions and fission reactions that we talked about in the 100 years ago.
hmm,
So when that happened, people essentially went, okay, suddenly we know what radioactivity is, and what radioactive decay is. So we can see particles are actually going from a heavier element to a less heavier element and going down the scale. So I guess once people started doing that, there was a thing about, oh, what would just happen if we just smash two things together and then see what comes out of it. And that's when I guess particle physics really began.
hmm.
Right. So then we were just like making particle accelerators, smashing things together, and then outpours everything.
Right, right. Okay. Tell me something. I'm sure you've come across this. I think I remember having this conversation with you at university about 10 years ago or whenever, about the theory of everything. Is that still a thing? Are people still pursuing it?
Yeah, people are still pursuing it. It's essentially, I don't know what the. I mean, there's various contenders like string theory and quantum mechanics. I mean, quantum mechanics is part of it, but
Hmm.
like string theory is one of the biggest, I guess, popular ideas. That how do you describe everything?
Hmm.
Because essentially, we want to make things simpler and simpler, and then we want to at the end have like one equation that describes everything.
Yeah. So
So
it's
I guess
happening.
that's research. That research is still going on. I think it's been going on for like 20 years, 30 or 40 years probably. Uh, and there's like, I guess like there's various ideas like string theory. Is the whole world a hallucination, or like I think Elon Musk believed that the whole world is a
The simulation theory?
simulation. Yeah,
Yeah.
yeah,
Well, that's not very
yeah,
helpful because then
yeah.
how do I, yeah, well, either way.
Yeah,
Yeah.
yeah, but then there's a lot of like ideas on how do we actually describe everything in one equation, and maybe string theory is one way of describing it. Bubbles are another way of describing multiverse ideas and all these kind of things. So there's a lot of work still happening, but I mean, it's going to take a long time to like prove any of this, right?
Hmm.
Until some alien comes to our planet who's like really high advanced and then tells us like, yeah, this is how it happened.
But is the math sound? I mean, how is this different from science fiction?
Yeah, yeah. I guess the science fiction part comes into play that we cannot actually prove it. We don't have the ability or the technology to prove it or test any of these ideas,
Hmm.
right? So that's where the science fiction part comes into play,
Okay.
right? Science fiction is only science fiction because we cannot make it.
For now. But yeah.
Yeah, exactly. For now, we made the mobile phone, and that was way back in Star Trek. People we had these like things on their hands, and then
Yeah.
we have we have things in our hands.
Yeah. Well, that's engineering fiction. So I mean,
Yeah,
yeah, I know
yeah.
it's called sci-fi, but it's like obviously it's ultimately for our humans' progress or whatever, the flourishing and
Yeah,
all.
and they're all based on like actual ideas as well, right? Even
Yeah.
even when like if someone like Archimedes or like Leonardo da Vinci was like talking about making drawings of helicopters and planes on his sketchbook in the 15th century,
Hmm.
I am sure like nobody thought that this would be actually something that would fly. It was
Hmm.
just this idea of like, oh, Da Vinci's drawn like something weird, like with wings,
Yeah.
in his
Yeah.
notebook, and then 500 years later, the Wright brothers are actually flying
Yeah.
stuff in the sky.
Yeah. I understand that sometimes, like, institutions are sort of formed to make guardrails against kooks. But I guess
Mhm.
that's not, sometimes kooks are important. Because I read a story like where Lord Kelvin was like, there's never going to be heavier than air flights. And there we go. I mean, New York
Yeah,
Times and
yeah,
every big, person who was an opinion maker was pretty doomy and gloomy about it. Everybody like, there's a massive status quo bias. But Wright brothers did it, and they were like they had a bicycle shop or whatever, right?
yeah,
So,
yeah.
sometimes it helps them not to sort of like be really imbued in all
Mhm.
the theory, although it's interesting, keeping an open mind.
And I mean, debate and like ideas which are not the same as the other person have always been like fundamental to science anyway. Like in most cases, right? I'm pretty sure half the people who worked on finding the Higgs boson did not believe that the Higgs boson actually existed. They were just like, well, I can prove it doesn't exist. Like, so they still want to work on it. The same thing with like quantum mechanics and, be it everything else in science. There's always been a good amount of healthy debate, even when you go back all the way to like Greek philosophers, right? These were all guys still debating like what is the fundamental laws of nature. One person believed it was this thing, and I guess that's where the philosophy comes in, right? Because it's been taken back to that. It was always philosophy that then turned into mathematics in a way of describing the world. So a
Okay.
healthy debate has always been, and a rivalry as well.
Hmm.
Like I feel like the best things to come out of science have always been because of rivalries
Yeah.
between scientists and egos between scientists.
No, but a healthy rivalry, because the kind of rivalry which, let's say you are an advisor for somebody and they are writing a paper, you are anonymous and they are not because they submitted a paper, and then you just don't like where this is going, and it tramples upon your
Mm.
like held ideas, and then suddenly the objectivity and the ethics go out the window when you try to like suppress them, and the like petty like tick, tick, tick culture comes in,
Yeah, yeah,
which I think that's an issue of like science funding, and I'm in favor of
yeah, and
more
it is.
prioritization. But yeah.
Yeah, and there's still a big thing in science. People and their egos, and because I guess that's one of the driving force, right? Because people are essentially, I want to be the smartest person in the room.
Hmm.
This is why I'm doing this thing, and that sort of drives
Yeah.
drives science forward because
Very,
someone else.
very second-handed drive, in my opinion, though. I mean, because if the whole point is conquering reality as opposed to conquering other humans, now that you need to be kind of humble about that. Humble in the sense you need to approach it in a humble way. So if what's really driving you that I'm the smartest in the room, you're in an Olympiad, man. Don't go do that. Don't do science or whatever. Like, yeah, I mean, that's just my opinion. But like, but yeah, those kind of rivalries can bring about, just because you hated somebody, that it could bring about that, as long as you don't go too far with destroying the person.
I mean, Newton is a great example of doing this. Like, you should read up his biography. He sort of like he was a guy who did not stand other people. Essentially, he brought people down. He brought people's like ideas down, and he invented maths to bring other people down.
Okay,
Essentially, so he was a
that's great. Inventing maths
so
for doing that is great, but then
yeah,
hiring an assassin might not be a good idea, or
yeah, yeah.
cancellation.
No, nothing like that. It was mostly reputational damage, and yeah, but he was a like I mean, he a great scientist. But if you read his biography, you can tell he was not a nice person.
Yeah. True that. True that. I Is there are there any competing theories apart from string theory? Because it seems to have taken so much oxygen that, like, if 40 years, if you haven't been able to prove it, then perhaps it's time to move on.
I think there might be a few other ones. I might have looked them up.
Oh no,
But
it's
yeah, I
fine. I mean,
think
it's just, yeah. I mean, it was mostly about, like, if the quest is still on and string theory is basically at an impasse, then
mhm.
there should be some other approaches. I don't know why there is a thing, but is that the ultimate quest then, to find the theory of everything?
Yeah, the theory of everything, where you can just like go from quantum mechanics all the way to the macro scale in one equation, right? That's probably the ultimate thing.
Do you think we are missing anything? Okay, let me ask you this. Again, this is going to be very speculative as well. Do you think the fundamental substrate of everything is material or energy? I'll tell you,
I
but for
guess
me, it's energy. I
that's
mean, that's why that's what I believe. I mean, of course, I'm open to be challenged, but I think it's energy. But what do you think?
yeah, probably it's like energy because I mean, as Einstein said, E equals mc squared. So
Yeah,
it's probably just energy that is being turned into mass or vice versa.
right.
And I guess the biggest blind spot, because I do have an astrophysics background, so I know I guess I learned about this more than the quantum mechanics side of it. So the biggest thing in astrophysics that's missing at the moment is still describing dark energy and dark matter,
Hmm.
where we still don't know what is currently happening out there in the universe. Because there's certain behaviors we see in galaxies and how the universe behaves where we're just like there's something missing here. There's like why so there's a big problem that they're trying to solve.
Hmm. Okay. And obviously, we are human beings with limited faculty and all of that. So
Mhm.
we are trying to understand it, but like we essentially want like a God's eye view on this. Um, do you think our perceptual abilities get in the way of this, or like how do we correct for all of that?
So technology is the biggest thing.
Hmm.
There's been vast, very big strides in technology in the past few decades, right? So we have better supercomputers, we have better telescopes being going into operation. There's a lot of things in play at the moment, from like X-ray telescopes to like ultraviolet telescopes to optical telescopes being deployed, radio telescopes. All these things are being deployed. Like James Webb Telescope just went up in the air a couple of years ago, last year, and
Hmm.
it's now delivering some results. So there's a huge amount of work being done now with like, because I guess Hubble was the big granddaddy of these things, right? It was used, the Hubble telescope, not Hubble the guy, but the
Hmm.
Hubble telescope. Although the Hubble the guy was also very influential in doing the Big Bang theory. There's a great book about that as well. Like you could look it up, just called The Big Bang, and there's a great summary of the whole argument and how people argued about what is correct, what's wrong. But yeah, the Hubble telescope was the big daddy of telescopes that was sent,
Hmm.
and that sort of helped a lot into understanding our view of the universe and what ideas we had of the universe and how accurate we were, how far away we were. There's a lot of like X-ray telescopes up there as well, which are helping out. But now with 20 years down the line, they're not good enough, and we know we have better instruments now to send up there. So hopefully, James Webb Telescope, which is up there, will help us solve a few more issues. The biggest issues in astrophysics are essentially obviously dark energy and dark matter, and also accurately actually measuring distances, because distances are enormous.
Hmm.
So the error bars can become really enormous as well.
Yeah.
And general relativity plays havoc on things.
General relativity plays havoc on things. Okay. So this and
Yeah.
general relativity is a theory which is describing gravitation or what else?
Yes, yeah. How gravity affects mass and everything around it, essentially. So, I like Einstein's famous equate gravity. Well, Einstein's famous experiment was, if there is something which is really massive,
Hmm.
it bends space time. If
Space
you think
time.
about
Yeah.
space time as a bed sheet,
Right.
and if you put like a ball in the middle, it will like deform the bed sheet,
Right.
right? And that's essentially the gravity, the mass of a star essentially deforming the bed sheet.
Right.
So if you throw a pebble around this deformity, it'll, instead of going straight, it'll deform and then do a ring around this deformity. So this is what gravity is, right? So we're circling a star because the sun is actually deformed space time, and now we're stuck. We're like trying to escape it, but we can't. We're just like circling around it.
I mean, deformed and or influencing it in such a way. But then why would they keep going around in orbits and not just essentially sink in? Because that's the ultimate thing that I common sense will tell me. Like the Earth is gonna like just basically sink into the Earth if that's how it's working and
Yeah,
it's not
yeah.
just something else.
Because there's
So
less conservation of mass, right? There's no really that much friction that is slowing the Earth's movement in space,
hmm,
and because space is mostly vacuum,
hmm,
so there's not really that much stuff slowing us down and making us fall into the star.
hmm,
So maybe we are probably are slowing down slightly,
yeah,
with each orbit, but
yeah,
probably be billions more years. So
yeah.
the sun will probably explode before we fall in. So
Oh, so the falling in parts is not entirely out of the question. It could happen, but you're saying the sun is going to
yeah,
explode first. All right.
yeah, probably.
Okay, either way, क्या हिंदी में ना कुआं and खाई, so fair enough.
Yeah,
Okay.
yeah, yeah. So things like the moon is moving further away from Earth every 2 centimeters per year. I think something
Hmm.
like that. It's
Okay.
quite small.
Right.
Or like 2 meters per year. I think this it's a quite small thing, but it's like every rotation is like moving away from Earth. So
Okay. So even the fundamental things that we think are basically always going to happen, they don't.
no, they don't.
And
Yeah, because there's
so,
always outside influence, right? We don't live like in a closed system.
hmm,
And that's another philosophical debate we can have if the universe is a closed system or not. But that's another question.
hmm. Yeah, 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 yeah. No, true. That's true. But I guess going back to the discovery of knowledge again, um, help me with some definitions. So theory versus law. Now there is a second law of thermodynamics. I'm like, I mean, is it a theory, a scientific theory, not like a theory in the humanities, but in a scientific theory, or is it a law? Why have that distinction? Just because is it just is it just branding?
So a law is something more fundamental than so a theory. Essentially, in science, is something you come up with, which is not proven,
I
right?
mean,
It's your
the,
theory, and then the law is something which has been proven experimentally. There's a lot of evidence to back it up, and then it becomes a law. Um, and obviously, this is not still not 100%, right? We
yeah,
could one day be like, oh, this one thing proves your law wrong, so it's not a law anymore. We got to check
right,
it out and find a new thing to
right.
explain it.
So they're
So
open to
even
that. The community
yeah,
knows that.
yeah. Oh, yeah, yeah. Like, I mean, Newton's equations of motions are probably one of the famous things where they explain a lot of things, but they can't explain the the movement of the planets around the sun. Right?
Right.
General relativity had to come in to explain why do the planets move around the sun in this particular fashion? Because there's slight discrepancies in what Newton's equations of motions tell us, and then how the planets actually were going around the sun.
So did Einstein like disprove Newton, or Newton is valid at a certain level of analysis and Einstein is
Yeah, yeah, yeah,
okay.
yeah. Newton is still valid in most cases, and only in like certain situations you can be like, oh, if you need more accuracy, then you go like, okay, I got to use like this thing now. So
Okay.
that's why we still teach like Newton's laws of motions,
Yeah.
right, to everyone who does a physics degree, because it's still very important, and you can still do a lot of fundamental science, a lot of fundamental physics just by that. And general relativity becomes really, really tricky and really hard. There's a lot of massive matrices you need to multiply out and all that kind of stuff. So
Yeah.
yeah,
Although I'm sure computers help with that
yeah,
multiplication.
yeah,
Yeah. Because
yeah.
the profundatory, I mean the not the profundity, sorry, the perfunctory work, which is like the just I don't know, brute force arithmetic. Great if you are great at that, but I want more creativity here because sometimes folks are so like disengaged with that basic chore, which can be
Mhm.
automated away that the creativity never comes in. I mean, it's just
Yeah. I think the problems with stuff like general relativity and special relativity, all these like and like quantum mechanics, all these ideas actually are is how do we actually make the student who's doing this course actually understand what's actually happening before
mm,
we tell them, oh, this program does it,
mm.
look at that. So I think most of our teaching is still based on here's the law behind it, here's how we got here, and then you can go from there, and then we can let them loose and read all the papers, then you can make your own models, computer simulations and all that kind of stuff. But yeah, it's really hard to like go into it, like
Mm.
actually like have an understanding of what it is. Like I think someone famously has said that, I think it was Einstein who famously said, if someone tells you they understand quantum mechanics, they don't understand quantum mechanics.
Yeah, I mean, I want to believe him, but again, like, I mean, he was a human being. He was into socialism. I'm not into that, and that's quite a stupid idea. But like, something he must have just said that statement in jest. I still think there is, of course, people okay, you are dumb and all that. People say that. I don't know. Maybe there is an issue with teaching as well. So there are teaching
Oh yeah,
ability.
yeah,
You know,
yeah, yeah, definitely. Like a lot of teachers haven't come up with better ideas on how to convey
communicate.
quantum mechanic communicate quantum mechanics. And I guess that's like stuff like Khan Academy
Mm,
does great. Like I did most of my revision on Khan Academy
okay.
because he was like such good at communicating the idea into how to do differentiating, how to do integration, how to do all these kind of different ideas that you learn in undergrad, but you might forget because you're always like trying to write stuff down, trying to pay attention in lectures.
Yeah.
And then when you go back to do the homework, you'll be like, oh, I didn't understand this
Right.
thing. Oh, how do I find out where it is?
Right. Okay. So just
But
before we close out the podcast, some
mm,
more fundamental questions that are fundamental to me. Do you know of the term Occam's razor, right?
mhm,
It's
mhm.
what is it exactly?
I think it's like so it's if something if there's a simple explanation for a thing, it's usually that, and
Yeah.
not the more complicated explanation for a situation, right?
So like fewer assumptions explaining like larger number of things compared to, you
Mhm.
know, you need to like assume more things in order to explain a fewer things. All right. Now, this is also like an injunction. I mean, like, how do we know this is true? This Occam's razor. We don't know,
Yeah,
right? So we
yeah.
just kind of accept it.
Yeah, and I guess it's for in most cases is the caveat they use, right?
Hmm.
And in most simple cases, probably the simpler explanation is obviously the best explanation. Like, why did I miss the train? Left the house late. So
Yeah.
that's probably the simplest explanation of why you missed the train. It wasn't because some guy bumped into you and then you like there was a traffic jam or something like that, right? It could be something as simple as left the house late. Um, but yeah, in many cases, especially when you complicate a model to explain something, that's when I guess Occam raises breaks down because now you have many factors affecting your situation, your model, your simulation.
Hmm.
Um, Fluid dynamics is a great example of this because there's a lot of different components that actually affect the flow of a fluid into a system. When you talk about formation of stars and planets, especially stars, there's like a ton of different types of things you need to take into account, from hydrodynamics to magnetism to gravity to particle sizes to what's the chemical composition of this gas cloud that is turning into a star.
Yeah.
All these things actually affect the formation of the star.
Right.
And if the cloud is too big, it might just turn into a black hole. So
Hmm.
you might not get a star at all. you know. So there's a lot of these things, and the more complicated the system, the less I guess Occam's razor is useful.
Okay. The journey from like getting an idea in the dream to hypotheses. And of course, you are doing a lot of subconscious things like looking at concretes, inducing either subconsciously or consciously. So creating the hypothesis, designing an experiment, testing out the experiment, the peer review process, which I have issues with, but either way, like the replication, and then
Mhm.
it becoming a theory, new things coming in the theory getting updated. And sometimes, although I don't think the community uses the word law anymore, I think it was like a branding thing when it comes to thermodynamics. So then it graduating to a law. Now, is this what a physicist or a scientist is essentially doing? Have I described this correctly? Is this a scientific method or am I missing
Yeah,
anything?
yeah, yeah. Yeah, that is a scientific method. You test an idea, you experiment it. The scientific method, uh, it should be able to explain something, and it should also be able to predict something,
Predict something.
right? It
Okay.
should use Yeah, so it needs to do these two things. And if it fails on one or the other, then it is not a viable idea essentially.
Okay.
Um, and you just need to start again.
Yeah. Yeah. What the funny thing to me is like all we're discovering these fundamental laws of nature, but we are still relying on heuristics, like rules of thumb, right? You know,
Mm,
if it's not predicting, then you're not basically it's not a theory. If it's not explaining and predicting, it's not a theory, and also things like the Occam's razor and all of those things. So it's weird, like what is the fundamental here? Like, okay, all right, but
yeah,
anything.
because I mean,
Go ahead.
the problem I think we have is that we don't live in a closed system. We live in a system which is always being influenced by something else, right?
Mm, mm,
The air we breathe, every time we breathe out the air, we are like chaos, right? It's that essentially entropy
yeah.
and chaos is
Yeah.
affecting everything. So there's no one way of explaining something. There's always be something influencing something else, and that just creates the issues we have.
Yeah.
And that's why heuristics are different, because you're like, oh yeah, I feel like when I do this thing happens, and if I do it 10 times, if it still happens, then I guess it's correct.
Yeah. Yeah. I mean, entropy has taken me into depression and gotten me out of it as well, because one could basically just think about, other ways of like enjoying life. But what entropy, apart from physics, has like basic, massive, I guess, implications, in my opinion. That's the reason you need to maintain your house, because otherwise things fall apart. And even if you do everything well, that isn't, it's in the nature of things to fall apart. But what I the interesting thing is it's not like a deterministic thing. They say it's probabilistic, right? It's a high probability.
Mhm.
Just you do this. You explain entropy to me in like a basic term, and then we'll see, and then we can close with that.
I guess entropy for me would be because we live in a chaotic world, always one thing always influencing the other. This probability comes from this chaos. So there is a high chance that you'll go to bed today and then wake up in the morning. That's pretty high chance. But there's a really small chance that when you go to bed, your roof collapses,
Hmm. Hmm.
right, and you die.
Yeah.
So entropy essentially is that there is high probability of doing the normal stuff always happening, but there's also a really, really small chance of like the really unexpected things happening.
Hmm.
You could wake up tomorrow and the sun might explode, even though
Hmm.
it won't.
Hmm.
Right?
Hmm.
I'm 99.99999% sure it won't explode tomorrow, but there's a small chance of that. And entropy is just a way of explaining these probabilities of um, how probable it is like this thing happening or that thing happening and that thing happening, and that can lead you down into a rabbit hole,
So does it
which is
say?
not good.
Well, I mean, no, go to the rabbit hole as long as you can keep. So that's the thing. We are always living. We don't know. We'll never have perfect information. And
Mm,
this is probably just my own personal education and the culture at that time I was raised in. There's a lot of like good boy, good girl, sort of like teacher's pet syndrome.
mhm,
Um, authority is good, but that's not where you get all the ideas from. Like ultimately, they need to
mm.
teach you how to like deal with reality on your own, which don't. We just
Yep.
rely on others, which is whatever. So we in this sense, I think entropy is a high probability of order turning back to chaos rather
Mhm,
than chaos turning back to order. But that can happen as well because that's what engineering is and that's what life is and that's what all of these
mhm.
things are. So, but eventually, order turns back to chaos and this dance keeps happening. And I guess one way you build stability and wealth and is to turn that chaos into
Mm.
order. Do you resonate with this definition?
Yeah, and I guess that you need to also, in that case, define what is order and what is chaos.
Okay,
It
well,
is what is one thing and what is the other thing as well, right?
that is true.
There's
That's
also
true.
another like fundamental philosophical question that we need to
Yeah,
think about
yeah,
is for us like having five pencils in a row, that's order. But
right,
having five pencils in a different directions, maybe that's chaos. But for
right.
someone else could be like, oh, that makes sense to me. That seems like order.
Okay. No. So
So
I'll take a radical stance here. I'm like a
yeah, yeah,
like
yeah.
like an egoist here. So this is for me,
Yeah,
who are
yeah, yeah.
human beings, right? So if I have a comforter in front of me, which I did not fold,
Mm,
and if it was just shreds of the material, to me that's chaos because I can't use it.
mm,
And the
mm.
comforter because I want keeps me warm, to me that's order. That's
Yeah,
me.
yeah.
It's very egoistic and I like it that way because yeah,
No,
human
no,
beings
that's
are doing
fine.
physics. So we should not forget that. Maybe ultimately everything is psychology. Who knows? I mean,
Yeah, yeah,
yeah,
yeah.
yeah.
Yeah, because I guess the in the because you have to think when you think about entropy in the massive universal scale, you need to think about what does the universe think is order or chaos? Does it think that the cooling of the universe that might or is happening is that chaos, or is that actually turning down the stove essentially? Is that chaos for the
Yes.
universe, or is that order for the universe?
Yes.
Because
Yes.
like we don't know. For us, when we look at our daily lives, we could have a messy table that's chaos, but we need to think about it in a perspective of the universe, and I guess the universe does not have a conscience, so or does it?
Yeah.
I don't know.
Or does it? Yeah. Because I was about to say that there are theories, even now scientific, the hard problem of consciousness and
Mm,
philosophical scientific theories, which they're like, we don't know. I mean, maybe we need to think of consciousness as a fundamental force, or I don't know.
mm,
Like, and then maybe everything pervades from there. That is interesting. But then some people say it's a cop out, but is it? Because you are assuming a few things. Those are the
mm.
axioms, right? Those are things that
Yeah,
everybody assumes and you build up from there.
yeah. I mean, at the end of the day, the standard model is still as much an assumption as anything else, right? We could still find something that will break it tomorrow.
Yes.
We could still do that. So as scientists, we know the laws we're working with, but we still need to be open with the idea that tomorrow someone will tell me something which will break this whole thing,
Yes. Yes.
and it'll fundamentally change how I think about things.
Yeah, yeah. And this is just my opinion, but I do think that when you have a certain amount of bureaucratic control over the scientific model and the way it might be disproved or sort of made better, then you'll have your, I don't know, with through various other petty Machiavellian reasons, you'll keep the model as it is just to satisfy yourself because you did your work over there, and then the actual thing which could kind of bruise your ego a little bit, but whatever. That's not going to come out. So I really hope that knowledge creation has to become open again. I mean,
Yeah.
yeah,
And I mean, it's also like it's also not an egotistic thing, but it also like something that maybe someone is like too scared to like face as well, right? We're all scientists are still humans, right?
of
It could
course.
just still be, it could still be that if someone goes down this path, they are already thinking, I cannot go down this path because my life will be ruined, or like I don't
Yeah,
think I can face the reality of discovering something, or
yeah.
disproving my own work, or disproving my colleagues' work, or something like that. So this is why we need, I guess, more egos.
We do, and we need to. For like scientists, they say they I want to be the smartest. And you're also trying to be the strongest in the sense, like actually
Yeah.
go fight, because that would be a nice sort of integration.
Yeah, I mean the amount of like people in science that are into like weightlifting and in gyms now is too high.
Yeah, that's good.
We, do,
It's
we,
good. That's a
we need
good
to we need to
train.
go back to our basements, man.
Yes,
Take me back to those days.
yes, absolutely. All right. Well, Godwin, this was great. Do you have any parting thoughts? Do you teach or study this still, or like do you connect with people, mentor them, anything like that?
Yeah, so literally yesterday I was in Leeds for an alumni meetup. So it was great to actually meet people and see what they've been up to. There's a lot of people still doing research in academia, so it was great to see them. Yeah, if anyone's interested in any sort of physics or science, just grab a popular science book. Start your journey from there. That would be my like best like suggestion.
Hmm.
And never stop being curious. Ask questions. I know as children we're taught by our parents to like don't ask hard questions,
Hmm.
right?
Ignore
At
them.
times, yeah, ignore them.
Yeah,
And then it's only when we grow up we actually start asking hard questions. But yeah, you should never
yeah.
like stop the child from asking hard questions.
Yeah, yeah, and it's okay to say that you don't know because parents are like, whatever. Okay.
Yeah, and that's the one thing we discovered as adults, that we're still learning things and we don't know everything.
Yeah, nobody's got this shit figured out. I mean, I
Yeah,
mean,
yeah,
yeah, we
and
that's a fundamental adult lesson.
and I think the earlier we not convince, but like confess to our kids, the better.
Yes, yes, yes. That definitely is the case. Just sorry, there's one last question before we stop the recording. Any popular science book which is not like dumbing down and like talking
Mm.
down to audiences, but is still explaining things in a relatively simple way, but also a good survey of all of physics, specifically science. Joy. Did you know? As
Yes. Okay. Okay. Let's see what there's obviously the famous thing is the Brief History of Time by Stephen Hawkins. It's like
yes. Okay.
phenomenal book. That's what got me into physics in the first place because I did not understand any of it. Uh, A Road to Reality is a great book. It's probably 1,200 pages long, and has a lot of things about physics in there. I can send you a list after this if you want to. There's also, if you want to know about the Big Bang theory, there's a book by Simon Singh called Big Bang. He
Hmm.
he goes through the whole history of going from a Earth-centric universe to an expanding universe and how this debate evolved. That's a great book. There's a book called Quantum as well, which is great about just the history of quantum mechanics. So these four are actually a really good starting point.
I will
But
include
yeah,
them in the show notes if you want to send them to me. But I'm
yeah, yeah,
definitely
yeah,
a road to reality even rings true to me. I mean, again, I believe in.
yeah. It's
Um,
it's a really big thick tome.
yes, 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 yes. Absolutely. I'm gonna do that. All right, man. Thank you very much for your time. I'm gonna stop the recording and we'll just debrief a little bit.
Yeah, no worries.
Bye bye.